Alright, this is video 13 on your integration techniques. So how do you know which integration technique to use? There's so many of them, right? So this is just like a simple, like when you see this, you do that. So the first thing you want to look for is to use a formula. Things like we did in video 12, okay? So your formulas that you know inside, outside, forwards, and backwards. So for example, if I have the integral of 5 over x dx, first of all, that's a constant, so I'm going to pull my 5 outside, and I'm at the integral of 1 over x dx. And I know the integral of 1 over x by my formula is just the ln of x, and I have 5 times that. And since I don't have limits of integration, I have to add my plus c. So I'm just using the formula that I know for natural log. The second integration technique is to find the area under the curve geometrically. So draw a graph and see if you can find the area under the curve by cutting it up into shapes. Things like what we did in video 11 were with the absolute value. We graphed the absolute value and we were able to find the area under the curve using the triangles. Now we're going to take the graph of square root of 9 minus x squared, which the square root of 9 minus x squared, you should realize that that's a circle of radius 3, but only the top part of it because it's just the positive square root. So if I have a radius of 3, my circle is going to look something like that. I mean, let's be real. I can't draw as well on this, but something like that. And I want to find the area under this curve. So then I'm going to say, okay, well, I can find this area under the curve using the area of a semicircle formula. So the area of a semicircle is 1/2 pi r squared. But keep in mind, I also want to find the integral from only 0 to negative 3, or negative 3 to 0. So I'm actually only finding this piece. So I'm not actually finding the area of the semicircle, I'm finding the area of the quarter circle. So I'm going to change this 1/2 to 1/4. So I have 1/4 pi, my radius is 3 squared. So this is going to give me 9/4 pi as my area. So that means that the integral from negative 3 to 0 of the square root of 9 minus x squared dx is 9/4 pi. And I'm pretty confident saying that's not just an approximation because I was able to geometrically draw it and I could see that everything that I'm shading in here is actually covered. The area is actually a perfect quarter circle. Technique 3 involves using a trig identity. So there's 3 trig identities you have to know or could be asked to use, but only one that like you have to know. Cold. Done. So that one is that sine squared x plus cosine squared x is equal to 1. If you know that one, you can get all the other ones because the other two come from dividing this one by either sine squared or by cosine squared. So, but you have to divide by the same thing, obviously. So sine squared, if I divide everything by sine squared, my new trig identity will become, 1 plus cosine over sine is cotan squared x equals 1 over sine is cosecant squared x. So I have sine squared, I'm going to just write them all down here. Sine squared x plus cosine squared x equals 1. I have 1 plus cotan squared x equals cosecant squared x. And I also have, if I divide now by cosine, how would that be different? I don't think I want to do that. If I divide by cosine squared x on all of them, then I'm going to have that tan squared x plus 1 equals secant squared x. So those are the 3 that you have to know, but as long as you know the first one, you can get the other ones. If you see something squared like this, like a cosecant squared or a cotan squared or a tan squared or a secant squared even, and you think it might be easier if you transfer one of these formulas into that integral instead, that will be helpful. So for example, in this integral, the integral of tan squared x, well, tan squared x, if I subtract this 1 on the other side, tan squared x is actually the same as saying secant squared x minus 1. Why would that be helpful? Well, the integral of secant squared is just tan. That's one of my formulas that I know. So I'm manipulating this integral to take out that trig that I don't know as well for the trig that I do know a lot better. So I'm going to change this integral to secant squared x minus 1 dx. And now I can integrate each part separately, right? So the integral of secant squared x is tan x, and the integral of minus 1 is minus x, and I have my plus c. Okay, so that was a lot easier than having to figure out how to integrate tan, because I don't know that rule as well. And even in this one, it's tan squared, so I definitely don't want to go down that road. So using trig to manipulate your integrals is another technique to help you solve these integrations that are going to be a little harder. The fourth technique is everyone's favorite. It's U substitution. I like to say it's like getting rid of a quotient or a product or a chain rule that needs to be undone, because it's when a function and its derivative are in the integral, so you can cancel out the derivative without any leftovers. But it's also really noticeable when you have things that are a product in general. So for example, x times cosine x squared dx, the integral of that, if you notice, if I take the derivative of x squared, I get 2x. And I have an x in my problem that I would need to get rid of. So I'm going to take u to be equal to x squared, which means when I do the derivative of u with respect to x, that gives me 2x. And I'm doing this so that I can replace all my x's with u. So I have this x that I can't do anything about, but I will cancel it eventually. That's the point. I have, let me move this down. The integral of x, I have cosine that I can't do anything about, but I change that x squared to u. And then I have this dx. Well, I have dx down here, so if I cross multiply and I solve for dx, then I get 2x dx equals du. And if I divide by 2x, then I could say that dx is equal to du times 2x. Let me move that so that I can write this here. So this, instead of the dx, I'm going to write du over 2x, which is what I want, because see what happens is this x cancels with this x. And this 2, that's a 1/2, that's a constant. That constant can be pulled out to the front. So this is just 1/2 times the integral of cosine of u du. And look how much nicer that is. I can tell you what the integral of cosine is. Remember that sine cosine trick I showed you in the last video? Sine cosine negative cosine. The integral of cosine is going backwards, so it's just sine. So this is 1/2 sine. Replace that u back. U is x squared plus c. Okay, so what is the purpose of this? The purpose is to get rid of all the x's, replace them with u's so that we simplify the integral, so that I can take the integral and then I put those x's back in when I substitute in for u to go back into my final answer. Okay, so that's just u substitution. Then we have u substitution's ugly cousin, the change of variable. It's rare, but it does come up, and if you want a 5, you have to know how to do this. So the change of variable is basically saying, okay, I'm going to let some stuff be u, but then I'm also going to might have to solve it in terms of x, and I might have to go back and forth in my integral. So here's the example. The integral of x, square root of x minus 2. This isn't a regular u sub, because if I take the derivative of x minus 2, it's going to give me 1. That's not going to cancel with that x. And if I take the derivative of x, it's not going to cancel with the x minus 2. If I take the u as the whole square root sign, then I have a chain rule involved, and that's not going to cancel either. So when things don't cancel, I can use change of variable. So for example, I'm going to let u equal x minus 2. And I'm only choosing that first because I'm assuming that since it's a little more complicated, it might give me some more options. So u is equal to x minus 2. So what would the derivative of u be? The derivative of u with respect to x is just 1. Now, when I substitute this in, this is saying that du is equal to dx, which is great, but I can't really get rid of that x then. So what is x in terms of u? Well, this tells me that u is equal to x minus 2. So I can solve this equation, u equals x minus 2, for x, and say that x is equal to u plus 2. So instead of the x here, I'm going to have the integral of u plus 2 times the square root of u, and I can replace that with du. Okay, so I can just distribute this now. The square root of u times u, remember u to the 1/2, so u to the 1/2 times u to the first is going to be u to the 3/2, because I'm going to add my exponents, plus 2 times u to the 1/2 du. And now this is just a simple integration. Add 1 to the exponent, divide by it. So u to the 3/2 plus 1 is 5/2 divided by 5/2. That 2 is going to flip up next to it. Plus 2u to the 1/2. Well, I'm going to add 1 to the 1/2. I get 3/2. And I'm going to divide by 3/2. That 2 is going to flip up and going to affect that other 2. Make it a 4. And I have my plus c, of course. So what does this make me get here? I have 2u to the 5/2 divided by 5 plus 4u to the 3/2 divided by 3 plus c. And I know what u is, right? U is x minus 2. So I could say this is just 2 times x minus 2 raised to the 5/2 divided by 5 plus 4 times x minus 2 raised to the 3/2 divided by 3 plus c. Don't simplify that. It's not worth it. Just leave it the way it is. Don't want to make any silly mistakes on simplifying. Okay? So that is your change of variables, u sub's ugly cousin. It doesn't come up very often. Usually you can use u sub. But just in case, you can manipulate that u to get your x in terms of u. Okay? And those are your integration techniques.